intermediate stage itself. Okay, that is electrophilic attack on benzene and cyclohexene. If you compare them, here all the bond lengths are 1.39 angstroms, and the C double bond C bond length is 1.33. Okay, 13 C13 shift are the same for benzene. Whereas simple alkenes, they are quite different. Okay, that is, if you take up the bromination reaction, we know that it is going to form anti-trans dibromo or anti-addition. Trans addition is taking place or epoxidation is possible. Whereas if you take the benzene and do bromination, it is not undergoing any reaction. What is the reason? Because the pi bonds are stable and delocalized. They are not available for the simple addition reaction. In such cases, what we had to do? Benzene can however be persuaded to react with bromine in the presence of a Lewis acid, like aluminium chloride can be used here. Okay, we can use aluminium chloride, which is a Lewis acid, for this reaction. Okay, in the absence of aluminium chloride only, the reaction was there with alkenes. Why? Because alkenes are more reactive when compared to benzene. Benzene, we require a catalyst. The catalyst used is aluminium chloride is the catalyst that is used. It combines only with very reactive electrophiles. Okay, that is, it gives substitution and not addition products are formed. Whereas here, in alkenes, only addition is taking place. It is nothing but electrophilic addition reactions, whereas in that is benzene or aromatic compounds, they are undergoing substitution reactions. Okay, that is clearly seen here. Electrophilic substitution on benzene in the presence of aluminium chloride. That is, an electrophile is created here. This electrophile, this is an electrophile, and it is going to attack on this one, converting this sp2 hybridized carbon. This carbon, all carbons in benzene are sp2 hybridized. They are converted into sp3 hybridized carbons. Okay, it is a saturated carbon. And after that is rearrangement, the hydrogen is shifted or removed, and it is going to form bromobenzene. It is what type of addition it is called as? Electrophilic addition reaction on benzene. Okay, what is the general mechanism? Is just attack of an electrophile. A sigma complex is formed and the loss of the proton. It is called as a sigma complex. Mesenhymer complex also, sometimes it is called as mesenhymer transition state. Okay, then it is undergoing. Why? Because it is having sp3 hybridized carbon is there. We know that sp3 hybridized carbon is a tetrahedral carbon. Attack of an electrophile to give an intermediate cation. Loss of the proton from the cation to restore the aromaticity. Aromaticity is again restored. That is the general mechanism. Okay, for any reaction, if you take nitration or Friedel-Crafts alkylation or Friedel-Crafts acylation or any reaction, that is sulfonation, all these are nothing but electrophilic substitution reactions on benzene. Aromatic electrophilic substitution reaction, they are called as. Nitration of benzene. What is important here? We require an electrophile. What is an electrophile? Electrophile is greedy of electrons. It is having more affinity for electrons. It is generally positively charged. Okay, there are some electrophiles which are neutral also. Okay, carbon CCl2, say dichlorocarbene. It is an electrophile. Okay, here HNO3 and H2SO4. This is called as nitration mixture. Nitration converts aromatic compounds into nitrobenzenes. NO2 plus is the electrophile. So that is, nitronium ion is the electrophile. How nitronium ion is formed? Why? What is the purpose of this sulfuric acid? Sulfuric acid is, the purpose is to dehydration of this HNO3. The purpose of sulfuric acid is to remove water molecule from HNO3. Okay, HNO3 is an acid. Both are acids, but sulfuric acid being stronger than this one, it can easily protonate this one in the first stage and later on it is removed. Yesterday we had seen if it is not going to leave, OH is not a good leaving group. Therefore, if it is not a good leaving group, what we had to do? We had to protonate it and remove it, that's all. Okay, protonation is easy to remove. Water is left over and nitronium ion is formed. See, this nitronium ion is a linear molecule, linear ion. Okay, it is linear in structure and isoelectronic with CO2, carbon dioxide, with sp hybridized nitrogen atom at the center. It is this nitrogen that is attacked by benzene, forming this sigma complex is formed, which is converted into nitrobenzene. Very simple. The electrophile is NO2 plus, called as nitronium ion. Okay, sulfonation of benzene. Benzene reacts slowly with sulfuric acid alone to give benzene sulfonic acid. One molecule of sulfuric acid protonates another and loses a molecule of water. Okay, both one sulfuric acid molecule is going to protonate the other molecule, and HSO3 is that is formed. This HSO3, okay, is the electrophile. Sulfur is the electrophile. This sulfur again that is undergoes deprotonation. This sigma complex undergoes deprotonation to give benzene sulfonic acid. What is the electrophile here? SO3 or bisulfite ion, HSO3 plus ion. Okay, HSO3 actually it is after removing this one, it should be that is OH is removed, and it is going to get this positive charge is removed, and this is developing positive charge. SO3 is the electrophile here in H2SO4, or else SO3H plus is the electrophile. This is about sulfonation. Friedel-Crafts reaction. This is a good example of SN1 electrophile is the tertiary butyl cation, which is regenerated from tertiary butyl alcohol. We know that tertiary butyl alcohol is an example for SN1 reaction. It is going to form a tertiary butyl cation. This cation can attack the benzene. The electrophile is this cation itself is the electrophile in the Friedel-Crafts alkylation. And finally, this alkyl benzene is formed. The reagent that we had to use is, the catalyst that we had to use is nothing but Lewis acid, aluminum chloride. What is the purpose of this Lewis acid is to generate this cation. This cation is generated here by removing this Cl as AlCl4. It is removed as AlCl4 minus. And this is the cation that is formed. This cation now attacks, and finally, this is nothing but Friedel-Crafts alkylation. We know from early stages of our studies only, we know about Friedel-Crafts alkylation, Friedel-Crafts acylation also is there. With acid chlorides and AlCl3 Friedel-Crafts acylation, it is called as Friedel-Crafts acylation. Why? Because this group RCO is called as acyl group. CH3CO, acetyl group. Okay, acetyl chloride is going to react with AlCl3 and it is going to form, this is the electrophile. RC triple bond O plus is the electrophile. Okay, this is the electrophile. Acylium cation. Okay, this is the electrophile, and finally minus HCl gives that is acylated benzene. If it's CH3, it is called as acetophenone. CH3CO unte dani emantam acetophenone ani antam. This is about Friedel-Crafts acylation reaction we had seen. Friedel-Crafts alkylation with the tertiary alkyl chlorides and Lewis acids gives tertiary alkyl benzenes. The more reliable Friedel-Crafts acylation with the acid chlorides gives aryl ketones. Okay, aryl ketones are, this is one of the most important synthetic importance. Dinki ekkuva importance undi antundi. Okay, then let us see about phenol, how the phenol is getting. We know that phenol is having a OH group. OH group, we know that it is a activating group, ortho para directing group. Okay, it is activating. Why? Because it can donate the electrons toward the benzene. What type of reactions we are seeing? We are seeing about electrophilic substitution reactions. Therefore, phenol group. Phenol, what is this phenol going to do? It is going to, that is, increase the electron density at the ortho as well as of benzene. Okay, at the ortho and para positions of benzene, it is going to increase the electron density. As a result, tribromo phenol is formed. Why? Because here the electron density is increased at ortho as well as para positions in the presence of bromine. Okay, it is highly reactive. OH ఉండడం వలన reactivity చాలా పెరిగిపోయింది ఇక్కడ. The OH group is said to be the ortho and para directing towards electrophiles. It is becoming a strong electrophile. No substitution occurs in either, that is meta position. Okay, phenol is going to react bromine in the presence of carbon disulfide. Instead of this tribromo, we have to deactivate it. Therefore, what are we doing here? We are using carbon disulfide so that monobromination takes place. Okay, monobromination is going to take place. If you see the mechanism of the reaction, here it is activating, and finally bromine is attacked at the para position. Para bromophenol is formed. Okay, why it is called as activating? Because of the resonance or mesomeric effect of this lone pair of electrons are involved in this resonance or mesomerism. Therefore, if you see, observe this one, the structure is having negative charge at the ortho as well as para positions. Therefore, it is called as ortho para directing group. This is about phenol substitution. Yes, why not in meta position? Means here we are having this minus charge only on the ortho and para positions. The electron density is increased at the ortho and para positions. What does an electrophile require? It requires electrons. It requires negative charge. Therefore, it will attack only at the ortho and para position. The electron-rich center is attacked, but not the less density containing meta is not attacked because of the difference in the electron densities. Observe this one. If you see this one, you can easily get the answer for your question. That is, why meta is not formed? Only ortho is formed. Minus charge is developed at ortho and as well as para positions. Ortho para lone attack outundi. Okay, nitration. Mononitration can be done. Single nitro compounds are formed para as well as ortho. Both mixtures are formed here in this reaction. Kolbe-Schmitt reaction is again important reaction. We know that here phenol is converted into salicylic acid. Here CO2 is the electrophile. Why CO2 is an electrophile? CO2 is an electrophile because C, that is carbon, is flanked or bonded by two oxygen atoms. Two oxygen atoms like this. These two oxygen atoms, what are they going to do? They are pulling the electrons towards itself. As a result, when they are pulling the electron towards itself, what is the charge developed on carbon? On carbon, the charge developed is nothing but positive center. Positive charge is developed on carbon. That is why it is an electrophilic carbon is developed here. CO2 and sodium salicylate, salicylic acid, it is important in the preparation of aspirin or aspirin. The sodium phenoxide is formed. Okay, phenoxide is more stable than phenol. We know that. Sodium phenoxide is formed, and this sodium phenoxide is going to attack the electrophilic carbon, and carboxylate sigma complex is formed, which rearranges to give or deprotonates to give the salicylic acid or sodium salicylate. Okay, that is about. This reaction is called as Kolbe-Schmitt reactions. Reacts with weak electrophile, carbon dioxide, though it is weak. Phenol is an activated compound. The reaction is called as Kolbe-Schmitt process. used industrially to prepare aspirin. Okay, amino, similar to phenol, similar to OH. NH2 group is also an activating group. It activates. Okay, yeah. What does the activating group means? It is ortho para directing group. That is why it is called as an activating group. Okay, therefore here 2,4,6 tribromo aniline is formed. Okay, what is again the same? The electrophile is bromine. Okay, there is no need of any of the catalyst. AlCl3 is not required here. Mono substitution of aniline. Simply acylate the amine. Okay, amine, as we had seen just now, it is again similar to phenol. What is going to happen? Tribromo, 3 areas it is going to attack. Even nitration also. For phenol, nitration takes place in simple conditions at 3 positions. 2,4,6 trinitrophenol. This 2,4,6 trinitrophenol is also called as picric acid. Simple acylate. Just what we have to do is, in order to make this highly active reactive aniline, we have to decrease the reactivity. How to decrease the reactivity? By acylation of the amino group. Okay, that is just by reacting with acetic anhydride or acyl chloride also, it gives this acylated aniline. Okay, and NHCO CH3. Okay, they are converted into form an amide. Okay, CONH2 is nothing but an amide. Okay, N-phenyl amide, acetamide. N-phenyl acetamide is formed here. This N-phenyl acetamide now is going to react with bromine. Only monobromination is taking place. It is stabilized. It is more stable again because of the delocalization that is involved here. Monobromination. This is very important. If you want to monobrominate aniline, what you have to do? You have to convert aniline into an acylated compound. Okay. Substitution in alkyl benzene. Toluene, though it is not having any lone pair, it is also called as an activating group. It is also called as an ortho para directing group. Okay, the reaction is known as sigma conjugation. Okay, why? Because the electrophile is attacked at this end. In a similar, this interaction is known as, here we know that methyl is having only sigma bonds, CH3. Even though it is having sigma bonds, it is activating. Earlier, if you had seen, in this phenol, there is a double bond that is created. Direct, that is delocalization or mesomerism is possible because of the delocalization of the lone pair of electrons. Whereas here in toluene, neither the electrons are there nor pi bonds are there. Only CH3 is having only sigma bonds. That's why this type of activating the benzene is called as by a mechanism called as sigma conjugation. That is the electron density at the ortho as well as para positions is increased here by this alkyl group. Cation stabilized by alkyl substituent. Okay, the electrophile is attacking at both, that is ortho or para positions. Okay, same as that of the earlier substitution reactions. Here also, that is para substituted, toluene is formed. Okay, ortho attack. If the electrophile were to attack at the ortho position, meta position, the charge would end in the delocalized over 3 carbon atoms. Okay, the delocalization on, that is on which carbon here? This is a meta carbon, is having positive charge. It is meta carbon positive charge. Therefore, electrophile will attack only at the either ortho or para positions. If it is attacking at the meta position, okay, so no stabilization by the alkyl group. The positive charge is not created at this carbon. This carbon is also called as ipso carbon. The carbon where the main substituent, the substituent is bonded, is called as this ipso carbon. Ipso carbon is not developing any positive charge. Okay, it is not developing any positive charge. Therefore, the substitution, it is not stabilized. This positive charge should be stabilized because of the plus I effect of this alkyl group. It is going to donate the electrons by sigma conjugation or hyper conjugation. We know that. Okay, that is why it is not going to proceed further. It is not possible. Okay, therefore, sulfonation of toluene. Okay, as the benzene we had seen, same as that of benzene, here also the SO3 is the electrophile, or HSO3 can also be acting as an electrophile. Okay, and it is going to attack at the para positions, same as that of phenol. Okay, phenol lagane ikkada kuda the sigma bonds are, that is pi bonds are involved, and it is going to attack forming a sigma complex, mesenhymer complex. It is called as, it is having both the charges, plus as well as minus charge. Here it loses the proton, forming an ion which is protonated, that is parasulfonic acid. Toluene parasulfonic acid is formed. Okay, toluene parasulfonyl. If it is Cl, it is called that tosyl chloride. Yesterday we had seen. Instead of OH, if it is Cl, it is called that tosyl chloride. Okay, chlorine sulfonic acid. If you take sulfuric acid, it is parasulfonic acid, it is called as. If you take instead of H2SO4, let us substitute one of the OH with chlorine. Okay, chlorinated sulfuric acid. And it is going to form again the same compound. It is called as a tosyl group. This is called as parasulfonyl, paratoluene sulfonic chloride. Paratoluene sulfonyl chloride, it is called as. Sulfonation of toluene. SO3 is the electrophile, and draw the intermediate with the charge at the ipso carbon to show the stabilization of the methyl group. The charge is there on the, therefore it is stable. This is about sulfonation of this one. What is aniline? Just now we had seen how to make aniline less reactive. Just by acylating it, it is going to convert into amide and it is becoming less reactive. Okay, in acylation takes place. Toluene we had seen. Sulfonation of toluene. Okay, it is electron withdrawing groups. How the electron withdrawing groups are going to affect this electrophilic substitution reaction? Electron withdrawing groups, for example, aniline in the presence of acid, it is going to convert into anilinium ion or tertiary, okay, trimethyl aniline or quaternary ammonium salt. What is happening here? Nitrogen is developing the positive charge. Even aniline also in the presence of acid, it is acting as a deactivating group. NH3 plus nitrogen paina plus charge undante chalu. Lone pairs ఉంటేనేమో NH2 ఉండాలి. రెండు substituents ఉంటే NH2 ఉన్నట్టయితే లేదా Me2 ఉన్నట్టయితే just it is acting as a activating group or the para-directing group, whereas here it is an electron withdrawing group, it is meta-directing group, it is a deactivating group. Okay, in the presence of sulfur, that is a nitration mixture, nitration takes place at meta position instead of para position. Major product is at meta position only. CF3 is also a deactivating group. The nitration, CF3 again meta. Okay, that is about all this. Unfavorable. If it is attacking at the para position, cations destabilized by this one. Positive charge is developed at the ipso carbon, but it is destabilized because of the. It is good. Why it is getting destabilized? Because the intensity of the positive charge is increased here. Electron withdrawing groups make aromatic rings more reluctant to undergo electrophilic substitution, but when they do react, they react at the meta position. Okay, at meta position only they are going to attack. That is about this. Then coming to halobenzenes, react more slowly than benzene itself. Halogens are ortho para-directing groups. Okay, then when there are two substituents like hydroxy are there as well as aldehyde group is there. The aldehyde directs meta. Aldehyde is nothing but a deactivating group, therefore it is directing the entering electrophile to the meta position, whereas OH is an ortho-para directing group. Okay, since OH is more powerful directing than methyl groups, it wins and directs the electrophile ortho to itself. Okay, when there is a, okay, therefore here this position is favorable. Why? Because it is ortho to this one, OH, it is ortho to OH, it is meta to aldehyde group. Okay, then ఇక్కడ మిథైల్ OH రెండు ఉన్నాయి మనకు. ఇక్కడ OH, ఓకే, OH ఏమో రెండు, ఇక్కడ దీనికి ఆర్తో అయితే ఇక్కడ, దీనికి ఆర్తో అయితే ఇక్కడ. OH is going to win. Why? Because it is strong. Okay, the ortho para directing nature or activating nature is more powerful for OH group than that of methyl group. Bromination of this amide goes ortho, but meta to the methyl group. Okay, here this is amide, this is methyl. Okay, therefore amide is going to win the race. That's why it is going to come at the ortho position. The aldehyde below has three groups, two methoxy group that direct ortho and para, and an aldehyde that directs meta. Main nitration product is ortho to this one, to aldehyde. Okay, why? Because there are two groups that are there. Therefore, it is going to attack at this position. When there are two activating groups, one deactivating group is there. Okay, only with stable cations it is going to work well. That is, Friedel-Crafts alkylation work well only with stable cations. If there are no stable cations, it is not going to work. Okay, that is about for alkylation. Friedel-Crafts use acylation. Friedel-Crafts reaction lo acylation route lo velli alkyl cheyadam easy anta. Okay, why? Because they can be converted. Okay, then it is more that is reactive. Acyl chloride is more reactive. Okay, that is why use acylation route rather than. Okay, first of all, what is done is acetyl chloride we are taking, or acyl chloride is, what is this one? Methane, ethane, propanyl chloride, AlCl3. It is going to form an, that is a adduct, and a electrophile acylium ion is formed. This acylium is going to form this acylated benzene. Acylated benzene can be by means of Clemmensen reduction. We can convert into N-propyl benzene. Okay, it is nothing but reduction, where it is this route is favored for preparing alkyl benzenes. Not only this one, we can use acetic anhydride also. Acetic anhydride, what is required here? Chlorine is a leaving group. Here, acetyl group is the leaving group. Okay, we can easily convert them. And for example, here we are preparing this 4-phenyl butanoic acid. In the presence of acid, it is undergoing cyclization. Okay, H3PO4 annihilation is taking place. Acylation is the product withdraws electrons from the pi system, making multiple substitution harder. The ring is too deactivated to start. Okay, why? Because here once alkyl benzene, we know that alkyl group is a ortho para directing group, whereas acyl group is a deactivating group. ఒకసారి acyl వచ్చిన తర్వాత ఇక మళ్ళా substitution జరగదు. Rearrangements are also no longer a problem here. Okay, that is nitronium ion. How the mechanism is involved in the nitronium ion formation is there here. NO2 plus etla form aitundi. Okay, this is the complex. Already we had seen this mechanism. Okay, I think you had understood some areas of this one, that is electrophilic substitution. Manaku ardhamaindi anukuntunna. Next, let us move on to other areas of nucleophilic aromatic substitution. ఎట్లుంటుందో చూద్దాం. Okay, how the nucleophilic aromatic substitution takes place. Had you understood? If you had understood type 1, if you had not understood type 2. Thank you, Shekhar. Now let us go for nucleophilic aromatic substitution. Here again we are having many mechanisms of there. Screen కనపడుతుందా? Okay, we are having a PDF of notes. మీకు కూడా మార్కెట్లో దొరుకుతుంది ఈ నోట్స్ ఈజీగా. నేను ఎప్పటిదో పాతది ఉండే. ఇది చూడండి, మనం డిస్కస్ చేయడానికి ఇది సింపుల్ గా అనిపించింది. ఓకే, nucleophilic substitution. It is again 3 types of nucleophilic substitutions are there. Can you see the screen? Hello students. Screen కనబడుతుందా? No. Okay. ఇప్పుడు okay, I think it is visible now. Can you see the screen? Screen కనబడతలేదా? Very good. Okay, aromatic nucleophilic substitutions. Let us see. Here, unimolecular aromatic substitution is there, bimolecular substitution is there. Another one is benzene mechanism is also there. Okay, here what we have to do is, we know about SN1 reaction and SN2 reaction. Okay, in SN2 reaction, if you see, what is going to happen? We are attacking the nucleophile, forming a pentavalent transition state. Okay, similar to that one, here also it is going to happen. Before that, let us see unimolecular. What happens in the unimolecular nucleophilic substitution? In unimolecular nucleophilic substitution, if we have taken tertiary butyl chloride, converting into a cation, it is converted into a cation like this. Tertiary butyl cation. This is a slow step. Formation of the cation is a slow step. It is called as unimolecular because the rate of the reaction is depending only on the alkyl halide. Okay, and this is attacked by the OH. OH minus, it is fast. Therefore, the rate of reaction does not depend upon the OH minus concentration in SN1 reaction. Similar to that, unimolecular aromatic substitutions also takes place, but they are very less in number because this cation is very less stable. Okay, this cation is less stable, and the repulsions between the pi electrons and nucleophiles are going to take place. Okay, that is why it is very less number of examples are there. Anyhow, we will see some of the examples where especially diazonium chloride salts. Benzene diazonium chloride on hydrolysis is going to give phenol. Okay, phenol we can prepare easily by this one. It is a what is the reaction mechanism? If you see, the loss of this N2 takes place in the first step. It is very slow step. Okay, the loss of nitrogen takes place in the first step. It is very slow in nature. And in the next step, the attack of this OH or H2O takes place. And finally, phenol is formed. Okay, phenol is formed like that. Then, if you see another example, Sandmeyer reaction, copper chloride. Okay, Cu cuprous chloride and HCl. This is nothing but chlorobenzene is formed. Again, diazonium chloride is going to show this reaction. And copper powder, Gutterman reaction, HBr. Okay, Br, bromination takes place here. H3PO2 and H2O, only benzene, hydrogen is attacked here. Okay, and here just now we had seen this reaction. All are nothing but AR-SN1 reactions. Okay, all are nothing but the examples of SN1 reactions only. Okay, then let us see some more examples where the chlorobenzene also, that is we can see this example of chlorobenzene. where chlorobenzene is going to be substituted by OH group, but the reaction is very slow. Okay, it requires very high temperature. It is also an example of nucleophilic substitution reaction. Okay, chlorobenzene. What is happening to this chlorobenzene? In the presence of NaOH at 300 degrees centigrade, very high temperature is required. It gives phenol. Okay, phenol is formed. What type of reaction it is? It is again the same type of reaction where
SN1.
SN1, that is AR SN1 reaction. Okay, and another one is here, especially in this such compounds, if at all an electron withdrawing group is there. Electron withdrawing group. What is the purpose of this electron withdrawing group? It is called a deactivating group. For example, para-nitro is there, or para-chloro-nitrobenzene. This nitro group, what is it going to do is it is going to stabilize. Okay, it is going to stabilize this charge. That is a nucleo. Okay, we are seeing about nucleophilic substitution reactions. In the presence of NaOH, it is going to attack, it is favoring this para attack. Okay. Why it is favoring? Because what is required here, a cation formation is important here. The cation form, it should be left over easily. Okay, therefore, Cl is easily removed. When for removing this one, electron withdrawing groups favor this ARSN1 reaction. That is one of the most important example which I had found in Morse and Boyd. These are the examples of ARSN1 reactions. But my dear students, you must remember that benzene diazonium chloride are good examples for ARSN1 reaction. Then another example, let us see another type of reactions are ARSN2 reactions, bimolecular substitution reactions. Maheshwari, what is your problem? Can you see this screen? Maheshwari? Screen anvadathaleda?
Yes, sir.
Okay.
Yes, sir. I can see the screen.
Okay. I will proceed. Here, ARSN2 reaction. They are bimolecular substitution reactions where what is going to happen in a general bimolecular in aliphatic compounds. Okay, we know that, for example, if you take a SN2 reaction, what is going to happen is if you are having chlorine like this and we are attacking OH minus, this OH minus and the chlorine are partly going to develop, the new bond is partially formed and the old bond is partially cleaved. A transition state where it is, okay, a pentavalent state is formed. What is the hybridization of this one? This carbon is again sp2 only. It is sp3 hybridized carbon and this is sp2 hybridized carbon. Why it is sp2? Because we require a plane in the middle and a lobes, p lobes are required on both lateral sides of this one. Then only it is possible. Okay, then it is going to leave this chlorine. Chloride is removed and finally it is going to form a Walden inversion. OH is formed on the other side. If it is dextro, we are starting with dextro compound, you are going to get levo. But one thing is it should be chiral. If you want to say it as plus means it should be chiral. Okay, then let us see about this benzene. Benzene derivative is also having this group and it is called as a leaving group here. In the presence of nucleophile, it is going to attack, okay, on the same carbon and forming a complex, okay, where this negative charge is that is moving or getting delocalized, and it is forming a substituted compound finally. Okay, this is about AR-SN2 type of reactions. Okay, in AR-SN2 type of reactions, again, if you are having or either SN1 or SN2 reaction, especially AR-SN2, if you are having electron withdrawing groups, it is always favoring this substitution. Why? Because NO2 like groups, they are going to remove the density or decrease the density of the negative charge. Okay, which is more reactive for this AR-SN2, because the more than NO2 groups, more reactivities. Here there are no NO2, only one NO2 is there, two NO2. Among these four, which is more reactive means this one is more reactive. Okay. Electron donating groups unte appudu reverse untadi. Okay, if electron withdrawing groups increase electron density, decreases very easily. Okay, then AR-SN mechanism, nucleophilic substitution benzene mechanism. It is also called as elimination addition mechanism. It is first of all eliminated, followed by addition. That is why benzene mechanism is also called as elimination addition mechanism. Okay. Here, what is going to happen is, this is the group that is we are having. It should have this hydrogen NH2 minus, especially sodamide. Okay. NH2 minus is acting as a base. It is removing this ion, that is H plus ion is removed, and minus charge is developed here. Okay, it is developing minus charge. This is our benzene, where this hydrogen is removed, and there should be a leaving group. That is the condition for this one. There should be a leaving group. In the presence of sodamide, Na plus NH2 minus. Okay, this NH2 minus is nothing but is going to remove this H plus. And finally, what is formed here? A anion is formed. Okay, anion is formed. Minus charge is developed here. There is a chlorine. And we are having again these bonds as it is. There is no delocalization. In the next step, this minus charge, this minus charge is going to be shifted, followed by the elimination of this chlorine. As a result, it is forming a benzene. A benzene is formed. A benzene is formed finally. Benzene is having same number of pi bonds. Along with them, one extra bond is there. A triple bond is there. How it is going to develop this one? By the overlap of the orbitals. Okay, that is, we know that each carbon is sp2 hybridized. Each carbon is sp2 hybridized. Therefore, it is having lobes like this. A p orbital, unhybridized p orbital. The interaction between them makes it more stable. This is called as benzene. Benzene is having a triple bond between them. This benzene, after formed, is attacked by this NH2 again. Okay, NH2 is going to attack this benzene. NH2 minus is going to attack this benzene, and it is going to form both, that is NH2 here and another isomer with NH2 at the other position. Why? Because there are two possibilities. Equal probability is there, 50%. Therefore, this proves that there is a benzene mechanism involved in this one. This is especially for amination it is used. Okay, this is called as benzene mechanism. Okay, and this is called as elimination addition mechanism also. Why? Because first of all it is eliminated. Cl minus is eliminated. HCl, H is eliminated, Cl. Therefore, elimination. After that, addition takes place. Okay, that is both are eliminated. H as well as chlorine, both are eliminated. After that, addition is taking place. Therefore, it is called as elimination addition reaction. Okay, you must have an idea about all these reactions also. Electron releasing groups. If there are electron releasing groups, then one is more than two. Okay, the group that is there. If there are electron releasing groups, we know that ortho substitution takes place. If it is electron withdrawing groups, two is more. Okay, this is observed even for these compounds like this. Just now we had seen this is an electron releasing group. This is a major product. Okay, this is OCH3. Methoxy group is there. It is giving anisodine and it is a meta product. OCH3 is a minus I affecting and dominates this one. Therefore, it is major product is meta. It is plus I affecting only, but it is giving meta. Here CF3 is also giving meta product. Okay, like this we can see any number of examples. These are about, this is about benzene mechanism. Okay, students, that is about today's class. In the next class, let us see about redox reactions, that is oxidation as well as reduction reactions. Let us see. Any doubts? Any doubts unte cheppandi. Ramesh sir? Shall I call another sir? ఇంకేమైనా డౌట్స్ ఉన్నాయా? ఏమైనా అర్థమైనాయా? I will ask you to unmute also. I think you can unmute yourself. కనీసం ఒక అవుట్లైన్ అన్న అర్థమై ఉంటుంది అని అనుకుంటున్నాను. మై పర్పస్ ఈస్ టు అట్లీస్ట్ డెవలప్ అన్ అవేర్నెస్, develop an outline of all the mechanisms. We had seen elimination mechanism, we had seen substitution mechanism, we had seen addition mechanism. Okay, in addition, we had the important rule is Markovnikov's rule. In elimination, we had seen Sedzeff rule as well as Hoffman product, Sedzeff product and Hoffman product. All those we had seen. Okay, definitely I will send everything that is there with me. Ramesh sir?
సార్ మీరు అన్మ్యూట్ ఉన్నారు సార్, మ్యూట్ ఉన్నారు.
కష్టపడండి, కష్టపడితే సీట్ వస్తుంది అని చెప్తున్నా. హార్డ్ వర్క్ చేయాలి బాగా. రమేష్ సార్ అసలు